Let's explore the correct method for sizing an air conditioner feeder and its overcurrent protection. We'll use the National Electrical Code, specifically sections 430.24, 440.22a, and 430.62 to guide our calculations. To begin, let's consider a single air conditioning unit with a rated load amperage, or RLA, of 16 amps. We will assume that there is no branch circuit selection current stated in the nameplate of the equipment. Our first step involves sizing the conductors. According to NEC section 430.24, the conductors supplying the air conditioner must have an ampacity that is not less than 125% of the motor's full load current, or FLC. In our example, the RLA of 16 amps serves as our FLC. Therefore, we need to calculate 125% of 16 amps. This calculation is 16 amps multiplied by 1.25, which equals 20 amps. The conductors must therefore have an ampacity of at least 20 amps. Now, we need to select an appropriate wire gauge. Referring to NEC Table 310.15b16, we can determine the ampacity of various conductor sizes. For example, 12 American wire gauge copper conductors with THHN insulation in a dry location and an ambient temperature correction factor considered typically have an ampacity of 20 amps. Thus 12 American wire gauge conductors are suitable for this application, as they meet the minimum ampacity requirement of 20 amps. Next, let's consider the overcurrent protection for the air conditioner. NEC section 440.22 addresses the rating or setting for the motor branch circuit, short circuit, and ground fault protective device. This section allows for the maximum fuse rating to be based on 225% of the full load current. In our example, this would be 16 amps multiplied by 2.25, which equals 36 amps. Therefore, a fuse rated at 36 amps would be the maximum size permitted at the disconnect switch. However, standard fuse sizes may not include a 36 amp fuse. In such cases, you are permitted to use the next higher standard size fuse, provided that it does not exceed the motor's ability to start and run without damage. Common standard fuse sizes close to 36 amps are 35 amps and 40 amps. It's crucial to consult the air conditioning unit's nameplate for any specific fuse recommendations from the manufacturer, as these instructions take precedence. Now let's address the feeder protection. A feeder is the circuit that supplies power to one or more branch circuits. In our scenario, the branch circuit serves the air conditioning unit. NEC section 430.62 dictates the requirements for the protective device for the feeder. Specifically, the section states that the feeder overcurrent protective device, such as a circuit breaker or fuses, shall have a rating not greater than the largest rating or setting of the branch circuit, short circuit, and ground fault protective device for any motor supplied by the feeder. In simpler terms, the feeder breaker or fuse cannot be larger than the breaker or fuse protecting the air conditioning unit itself. In our example, we determined that a 36 amp fuse, or potentially a 40 amp fuse depending on the standard sizes and the manufacturer's recommendations, would be appropriate for the air conditioning unit. Therefore, the feeder protective device, such as a circuit breaker, must be rated at 40 amps or less. A 40 amp circuit breaker would be a suitable choice in this scenario. To summarize, based on our analysis and application of the National Electrical Code, the air conditioner feeder should be sized using 12 American wire gauge conductors. These conductors are adequate because they have an ampacity of 20 amps, which meets the requirement of being at least 125% of the air conditioner's 16 amp RLA. The feeder should be protected by a 40 amp circuit breaker or fuses. This rating is appropriate because it does not exceed the rating of the branch circuit overcurrent protection for the air conditioning unit. Remember to always consult the specific nameplate information on the air conditioning unit and to adhere to all applicable local and national electrical codes. It's also recommended to consult with a qualified electrician for any electrical work to ensure safety and compliance. Let's go into a bit more detail about conductor ampacity and how it's determined. Conductor ampacity refers to the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code provides tables, such as Table 310.15b16, that list the ampacities of various conductors based on their size, insulation type, and installation conditions. Several factors influence a conductor's ampacity. These include the conductor's material, typically copper or aluminum, the conductor's size, expressed in American wire gauge, the insulation type, such as THHN, THHW, or XHHW, the ambient temperature, which is the temperature of the surrounding environment, and the number of conductors bundled together in a raceway or cable. When selecting conductors for an air conditioning unit, it's crucial to consider these factors to ensure that the conductors are adequately sized to handle the load. If the conductors are undersized, they can overheat, leading to insulation damage, reduced efficiency, and potentially fire hazards. Now let's delve deeper into the overcurrent protection requirements for air conditioning equipment. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can result from short circuits, ground faults, or overloads. The NEC specifies the maximum allowable overcurrent protection for various types of equipment, including air conditioning units. The primary purpose of overcurrent protection is to prevent damage to the equipment and wiring, as well as to minimize the risk of electrical fires. When selecting overcurrent protection for an air conditioning unit, it's essential to consider the unit's full load current, the motor's starting characteristics, and any specific requirements outlined by the manufacturer. NEC Section 440 provides detailed guidance on overcurrent protection for air conditioning and refrigeration equipment. It's important to note that the overcurrent protection requirements for air conditioning equipment may differ from those for general motor circuits. This is due to the unique operating characteristics of air conditioning compressors and the potential for high inrush currents during startup. Furthermore, the location of the overcurrent protection device is also critical. Typically, overcurrent protection is provided at the point where the conductors receive their supply, such as at a panel board or disconnect switch. This ensures that the entire circuit is protected from overcurrent conditions. Let's clarify the difference between branch circuits and feeders in an electrical system. A branch circuit is the circuit that extends from the final overcurrent protection device to the outlets, lights, or equipment being served. In our example, the branch circuit would be the wiring running from the circuit breaker in the panel board to the air conditioning unit. A feeder, on the other hand, is the circuit that supplies power to one or more branch circuits. The feeder originates at the service equipment, such as the main panel board, and distributes power to subpanels or individual loads. Understanding the distinction between branch circuits and feeders is crucial for proper circuit design and overcurrent protection. Each type of circuit has its own specific requirements for conductor sizing and overcurrent protection, as outlined in the NEC. When sizing feeders, it's important to consider the total load served by all of the branch circuits connected to the feeder. The feeder conductors and overcurrent protection must be adequately sized to handle the combined load of all the branch circuits. Now, let's discuss the importance of consulting the air conditioning unit's nameplate information. The nameplate is a metal or plastic label affixed to the air conditioning unit that provides essential information about the unit's electrical characteristics. This information typically includes the rated voltage, full load current, minimum circuit opacity, maximum overcurrent protection, and other relevant data. The nameplate information is critical for proper circuit design and overcurrent protection. It provides the specific requirements for the air conditioning unit, as determined by the manufacturer. Always refer to the nameplate information before selecting conductors, overcurrent protection devices, or other electrical components for the air conditioning unit. If there is any conflict between the NEC requirements and the nameplate information typically takes precedence. In addition to the NEC requirements, it's also essential to comply with all applicable local electrical codes and regulations. Local codes may have additional requirements or restrictions that are not covered in the NEC. Always check with the local electrical inspector or building department to ensure compliance with all applicable codes. Furthermore, It's recommended to consult with a qualified electrician for any electrical work, especially when dealing with air conditioning equipment. Electricians have the knowledge and experience to properly size conductors, select overcurrent protection devices, and ensure that the electrical system is safe and code compliant. Working with electricity can be dangerous, and it's always best to leave electrical work to the professionals. Let's also discuss the importance of proper grounding and bonding in air conditioning circuits. Grounding is the process of connecting the electrical system to the earth, providing a low impedance path for fault currents to flow back to the source. Bonding is the process of connecting metallic parts of the electrical system together to create an electrically continuous path. Proper grounding and bonding are essential for electrical safety. They help to minimize the risk of electric shock and reduce the likelihood of electrical fires. The NEC provides detailed requirements for grounding and bonding in Article 250. It's important to follow these requirements carefully to ensure a safe and reliable electrical system. In air conditioning circuits, grounding and bonding are particularly important due to the presence of metallic enclosures, refrigerant piping, and other conductive components. These components must be properly grounded and bonded to prevent them from becoming energized in the event of a fault. To summarize, proper sizing of air conditioning feeders and overcurrent protection requires a thorough understanding of the NEC, the air conditioning unit's nameplate information, and applicable local codes. It's essential to consider factors such as conductor ampacity, overcurrent protection ratings, branch circuit and feeder requirements, and grounding and bonding. Always consult with a qualified electrician for any electrical work to ensure safety and compliance. Remember that electrical codes and regulations are constantly evolving. It's important to stay up to date on the latest changes and to consult with qualified professionals for guidance. By following these guidelines, you can ensure that your air conditioning system is safe, reliable, and code compliant. Now, let's consider some additional scenarios and examples to further illustrate the principles of sizing air conditioning feeders and overcurrent protection. For instance, what if the air conditioning unit has a higher RLA, say 20 amps instead of 16 amps? In this case, the conductor ampacity would need to be increased accordingly. 125% of 20 amps is 25 amps. Therefore, you would need to select conductors with an ampacity of at least 25 amps. 10 American wire gauge conductors with THHN insulation typically have an ampacity of 30 amps, which would be suitable for this application. The overcurrent protection would also need to be adjusted. 225% of 20 amps is 45 amps. Therefore, a 45 amp fuse or circuit breaker would be the maximum size permitted. However, since 45 amps is not a standard size, you could use the next highest standard size, such as 50 amps, provided that it does not exceed the motor's ability to start and run without damage. Another scenario to consider is when the air conditioning unit has a branch circuit selection current specified on the nameplate. The branch circuit selection current is the current used to select the branch circuit conductors and overcurrent protection. If a branch circuit selection current is specified, it should be used instead of the full load current when sizing the conductors and overcurrent protection. For example, if the air conditioning unit has a full load current of 16 amps but a branch circuit selection current of 20 amps, you would use 20 amps as the basis for your calculations. In this case, the conductor ampacity would need to be at least 125% of 20 amps, which is 25 amps. The overcurrent protection would need to be sized based on the branch circuit selection current as well. Another important consideration is the ambient temperature. The ampacity of conductors decreases as the ambient temperature increases. If the air conditioning unit is installed in a location with a high ambient temperature, you may need to direct the conductor ampacity accordingly. The NEC provides tables and guidelines for directing conductor ampacity based on ambient temperature. It's also important to consider the voltage drop in the circuit. Voltage drop is the decrease in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause the air conditioning unit to operate inefficiently or even fail to start. The NEC recommends limiting the voltage drop in branch circuits and feeders to a maximum of 3%. To minimize voltage drop, you may need to increase the size of the conductors. In addition to the technical aspects of sizing air conditioning feeders and overcurrent protection, it's also important to consider the practical aspects of the installation. For example, you need to ensure that the conductors are properly supported and protected from physical damage. You also need to ensure that the overcurrent protection devices are readily accessible and properly labeled. Furthermore, it's important to maintain accurate records of the electrical installation, including conductor sizes, overcurrent protection ratings, and circuit diagrams. These records can be helpful for future maintenance and troubleshooting. Finally, remember that electrical safety is paramount. Always follow safe work practices when working with electricity, and never take shortcuts or compromise on safety. If you are not comfortable working with electricity, it's best to leave the work to a qualified electrician.